Our presenter is Alana Koser. Alana has worked as a thermal engineer on small satellites for the Space Mission Systems team at Sierra Nevada Corporation for over 6 years. Her degree is in mechanical engineering from the University of Washington. Welcome, Alana.
Thanks for the introduction. Hey everyone, thanks for joining my presentation. I'm going to talk to you today about SNC's heat rejection analysis process for early thermal assessment. In this presentation, I'll step you through the analysis description, the model setup, and how to use the results. The intent of this analysis is to answer the question, how much power can the bus reject if all available unblocked structure is used as radiator area? It allows for a comparison of total spacecraft heat rejection capability and individual panel capability so that you can compare it back to the applied heat load. I use this method at the beginning of space programs or during proposal efforts to provide early identification of likely thermal problems, inputs on desired spacecraft bus component locations, and approximate heater power needs without needing to build a detailed thermal model. It's useful because it prevents time and resources from being used on building the detailed model too early in the program when the design is inevitably going to change. It also allows for early thermal inputs on the design that may be missed if a detailed model is built only after the vehicle level designs are in place. This method has been used successfully for low Earth orbit and geo environments for bus sizes that are approximately a few feet in each dimension. Different bus sizes might require a different bulk average temperature than what I use here, which is 30 C. It's important to note that this method does have limitations, and design decisions made based on these results should be considered preliminary. Holding the spacecraft at a bulk average temperature inherently assumes perfect heat spreading, and it's an indicator of what's possible and may inform the analyst on whether heat straps or heat pipes are needed to move heat to adjacent panels, but it will not tell you if a heat pipe or spreader is needed within an individual panel. It also won't account for spacecraft gradients or orbital temperature swings, and it does not predict component temperature. For this analysis, I hold the spacecraft panels at a bulk average temperature of 30 degrees C with boundary nodes. The heat rejection capability is the power required to hold that temperature or the heat load into the boundary nodes. Even though most components can get much hotter than 30 C, the bulk average temperature, as I said on the previous slide, it doesn't account for spacecraft gradients or orbital swings. Dissipating components are generally hotter than the radiator, and cooler sections of the radiator have less heat rejection capability. And certain components, such as batteries, have narrower limits than other components. Therefore, the low bulk average temperature of 30 C often is a better indicator of actual heat rejection capability, even when a lot of components have a high limit of 61 C. I've done this analysis approach at SNC using the 30 C and also 40 C or 50 C boundary node temperatures, and I've observed that the 40 C and 50 C temperatures tend to overpredict the heat rejection capability. For a heater power approximation, first you would add MLI to the heat rejection model so that the heat rejection capability is 125% of the total contingency heat load. The additional 25% factor is to allow margin for any changes that occur between the preliminary bus configuration and the final one. Some components may be moved or entirely replaced, or the total power dissipation may turn out to be higher than originally estimated. Once the MLI configuration has been estimated, the cold case should hold the panels at a bulk average temperature of 0 C, or you could use a different temperature based on your overall bus temperature requirements. The heater power is then the power required to hold that temperature with the current best estimate heat load removed. This analysis makes use of a low fidelity model with only the external surfaces and external components modeled to account for radiator blockage and view factors. The internal components are represented with boundary nodes and are not modeled discretely. For this paper, I modeled a generic satellite bus, and it was only 272 nodes. I used boundary nodes to hold the bus at a bulk average temperature to capture heat rejection capability at that temperature. There's a number of ways to accomplish this. For this example, I built the model using solids that have 2 nodes through the thickness, with the internal facing nodes held as boundary nodes. It's important to note that Thermal Desktop applies environmental heating rates as a heat load on the external nodes. So if the boundary nodes are exposed to the external environment, that heat load will include the environmental heating rates in addition to the power required to hold the temperature. So you'll need to subtract out the heating rate. For this slide, I'm going to demonstrate how to use the results of the analysis. For this example analysis, I only looked at 3 beta angles, as shown on the images to the right. The attitude analyzed was a nadir pointing payload with the positive y pointing towards the velocity vector. Biased environments and optical properties for the hot and cold cases are stacked using the same methods as a traditional bounding thermal analysis that uses a detailed model. The table here shows the results of the heat rejection analysis for the example beta angles alongside 3 example cases of panel by panel bus dissipation. Note that the positive Z panel has a negative minimum heat rejection capability. That indicates that environmental inputs are higher than the radiation to deep space during at least one part of the orbit. In case 1, each panel has sufficient orbital average heat rejection capability for the components mounted to it. The panels might still require heat pipes or heat spreaders, but overall, the thermal design isn't likely to be overly complicated. Additionally, depending on component sensitivity, orbital variations may require additional thermal management of components mounted to the positive Z panel due to the instantaneous negative heat rejection. In case 2, the plus and minus Z panels and the launch vehicle panels all have more heat load than they can reject. In addition, the total heat load of 840 watts is higher than its heat rejection capability of 732 watts. So for this design, the bus structure doesn't provide enough radiator area and more may need to be added. You could also try to look at some creative solutions to either increase the heat rejection capability or lower the heat load. For case 3, the plus and minus Y panels have more heat load than they can reject, but overall the bus capability is sufficient. So these problem areas can be mitigated either by moving components around within the bus or by using heat straps or heat pipes to move the heat load from the plus and minus Y panels to the adjacent panels that have extra capability. This table shows the results of the heater power approximation for case 1 from the table on the previous slide. MLI was added so that the minimum heat rejection at 30 C still exceeds the contingency heat load for each panel. That's the top section of the table there. The section labeled 0 degree power requirement shows how much power is required on each panel in order to hold the bus at 0 C bulk average temperature. The heater power required is the max power requirement minus the CVE heat load, as shown on the bottom row. So the overall estimated heater power in this case is 66 watts orbit average, and you can see the panel by panel breakdown in the table at the bottom there. Note that the max heater power will be at least 25% greater than the orbit average once individual heaters are sized. This table here shows a comparison of the results of a low fidelity heat rejection model with a high fidelity traditional model, as well as a 1-node model calculation based on the 3rd edition of SMAD's spherical satellite analysis. For radiator requirements, all 3 methods agree very well with each other, but they don't agree as well for heater power. The heat rejection model is conservative, though, and provides a rough early approximation. This data is from an SNC program where the heat rejection model was used for estimates in the proposal phase. So in summary, SNC has developed a standard method to quickly assess a proposed bus configuration, and this method has been used successfully during proposals and early phases of a program to provide early identification of likely thermal problems and provide early input on desired spacecraft bus component locations and approximate heater power needs without needing to build a detailed thermal model. Does anyone have any questions?
All right. Thank you, Alana, for your presentation. Let's see. Let's go to Warren to see if we've got any questions yet in the chat. There might be a slight delay.
Yeah, let's wait a minute. I don't have any questions coming through just yet. Okay, why isn't the analysis done for higher beta angles where there isn't any eclipse?
So for an actual program, I would do the higher beta angles. It's just for this example case, I didn't want to have so many, so I only did the 3.
Alana, this is Bill. Hopefully this is a decent question. I apologize if it's out of context, but so this type of assessment, is this kind of modeling part of a model-based systems engineering approach to developing your programs?
Are you talking about just like configuration management type of stuff?
Well, I at Sierra Nevada, of course, I'm not really familiar with their approach to systems engineering. I know model-based systems engineering, where they go through the systems engineering process and utilize different, combination of models, maybe thermal models or structural models, or, like say system level models, like something done in Simulink or something like that, to sweep different inputs, different parameters to help define the overall design early on in the process. I was wondering if this particular type of modeling was part of that process, or if this was more standalone. Like I said, I wasn't sure that was a good question necessarily, but I was just curious if there was a connection to any model-based systems engineering methods that took place at Sierra Nevada.
So it's not, but I would normally do like a peer review where I make sure that all of my inputs into the model are correct.
Okay, thank you.
Yeah, so could you elaborate on how the analysis is used to position bus components?
Yeah, let me go back to, let's see. All right, so for case 3, you can see that the plus and minus Y panels have too much heat load on them. So you could take components off of those 2 panels and put them onto panels where they have extra heat rejection capability that they're not using. So like this positive Z panel here, it has a capability of 86 watts and it's only using 10 watts. So you could take 76 watts worth of components off of the negative Y panel and put it on the plus Z panel. Does that answer your question?
There's going to be a little bit of a delay. This is a question coming from Eric.
Okay.
And Eric says, yes, thank you.
I have another quick question, hopefully a little more straightforward than my last one. Sorry about that. This process that you've applied here, about how many times have you used it on different projects? Have you applied this same process?
Probably at least 7 or 8, but a lot of those were, they were proposal efforts or something, or we haven't gotten to the flight phase yet. So in terms of actually being able to compare this reduced fidelity model to the results of a detailed model, I would say only like 2.5 times.
Okay, well that sounds like it's been a real useful tool for you folks, and you definitely have some experience with learning how to apply it best.
Yeah.
Okay, we'll give the chat another minute or so here to see if there's any last minute questions. As a reminder, if anyone has any other questions after this presentation's over with, you can email the author or you can email the main TFAWS email address with your question. Just remember to include the presentation and the author's name, and we will forward on to them.
Yeah, so another question from Seth. Is the analysis ever done with higher beta angles where there isn't any eclipse?
Yes. Usually I do it with like a full beta sweep.
Okay, and this question's for me. Typically when you do your beta sweep, what's the resolution on the beta angles? Is it every 5 degrees, 10 degrees?
It depends on like the bus orientations and how much I think that things are changing. But typically I would do like 0, 30, 60, 90, and then the beta angle where you just barely don't have eclipse.
Right, okay, thank you. Another question from Eric. How sensitive are the results to radiator panel thickness and thermophysical properties?
They're not sensitive to that at all because so at the beginning I talked about how it assumes perfect heat spreading, and so it can't capture things like whether you need heat pipes or a heat spreader. So it only captures a theoretical what's possible, and the thermophysical properties won't really impact things.
Okay, thank you.